PU2 champions, welcome to Dhurandhar series, and in today's class we are going to do the one shot revision of the first chapter of chemistry, that is solutions. So my dear children, this chapter is super easy and a highly scoring chapter. You will be just getting 1 3-marker theoretical questions and 2 numericals and some MCQs. So this chapter is completely based on your concepts. If you have understood the concepts in a proper way, you can answer any question. Okay, so let's get started and see what we have in today's class. So first of all, we'll see what all topics we are going to cover today. The first thing we'll discuss like what is solutions and what are its types. Next, we'll talk about the concentration terms. Then what do you mean by solubility? Here you will study about solubility of a liquid in a liquid, solubility of solid in a liquid and gas in a liquid. Okay. Next, we'll talk about Henry's law. This is very important question. Then we'll also talk about Raoult's law. This is super important. Then ideal and non-ideal solution. Every year we get questions from here. Then we'll talk about azeotrope and yes, colligative properties, the heart of this chapter. Okay, this is super important and your numericals will be based on this colligative properties. And lastly, we'll talk about abnormal molecular mass. Okay, so let's start with what is solutions. So all of you might have heard this term millions of times, a solution. Okay, see, solution is a mixture of two components, okay, two or more pure substances. Now when you have only two substances, we call that type of solution as a binary solution. Okay, and in a solution there are two parts, that one is your solute and the other one is a solvent. And there are some basic, like you might have also seen what is like difference. Okay, so the size of the particle in the solutions must be less than 1 nanometer. Okay, and they exist in the single phase, means there will be not a gas state, a solid state, it is either in one state. Okay, it can be the whole component, the whole mixture can be in the liquid state, solid state, anything, but in only one phase. But here we are going to study about the liquid solutions in the whole chapter. Okay, let me make you clear that. So what is a solution? It is a homogeneous mixture of two or more substances. Now when we have two pure substances, we call it a binary solution. A solution has two components. The first one is solute and then we have solvent. Now what is a solute? Solute which is being dissolved, okay, which you are adding, and typically it is in smaller quantity. And what is solvent? The dissolving medium, the one in which you are dissolving, that medium is called as solvent, and typically that is in larger quantity. Okay, now the point here of writing typically is that it is not always true, but yes, it is 99.9% true. But you can have solutions where the solute quantity is more, solvent quantity is less. That is possible but very rare. Now examples of solute is like sugar, salt, anything, and solvent is like water, milk, etc. Now here what you can do, as you see, solute, sugar is added to the solvent and finally we get a solution. So sugar plus solute is equal to solvent, a solution. Okay, so how I can write this equation? I'll write in this word like solute. Okay, you can write solute plus solvent. Okay, gives you solution. Okay, now let us talk about the types of solutions. So basically, first of all, the solutions can be divided into two parts: dilute solution and concentrated solution. Dilute solution is where you have large amount of solvent relative to the solute, means solute is very less and solvent is very more. Okay, that is called dilute solution. Now concentrated solution contains a small amount of solvent relative to the solute, means the solute and solvent, like the difference is not very much. The solute concentration is in parallel or in a significant amount as compared to the solvent concentration. Okay, now we have aqueous solution. So if you have solvent is water, then we call it an aqueous solution, and if the solvent is any other substance like benzene or any other inorganic solvents, anything like anything except water is called as a non-aqueous solution. Okay, now in the solution I told you we have two parts, right? Okay, just a minute, sorry. See, in the solution we have two parts. What is it? One is your solute and the other one is solvent. Now, based on the physical state of the solvent, gas, liquid and solid, we can have different types of solution. Now whatever is the phase of the solvent, that is the, I can say it is called that solution. For example, if you see, gaseous solution will have gaseous solvent. In that the solute can be gas, liquid and solid. Similarly, liquid solution means the solvent will be liquid. In that you can have gas, liquid and solid as the solute. Similarly, in solid solution you will have solid solvent, and the solute there can be gas, liquid and solid. Now if you see here, first of all, if I am having an example of gas in gas, means solute is also gas, solvent is also gas. Example, I have mixture of oxygen and nitrogen gas. If you have liquid in a gas, you can have chloroform mixed with nitrogen gas. Okay, then you have solid in gas. Okay, you can have camphor in nitrogen gas. So these are different examples. Now, why this table is very important in MCQ section? Okay, easily questions are asked which of the following is an example of gaseous solution, or if I'll say if there's a gaseous solution, then camphor is the solute, then what will be the solvent? So like that, so many examples questions can be asked from these examples. Okay, and these types of solutions. So please, very very important, memorize this table. Okay, you can easily get MCQ questions, or even in 3 marker, like 1 marker question can be asked from this solution, and teachers know that this is very confusing to remember, so definitely they put question here to test your knowledge. So please prepare this table thoroughly. Okay, very very important. Now let's move to understand that what is concentration terms. Okay, so see, concentration terms means what? It tells us about how to tell how much solute is present in a solution, how much solute is present in a solvent or solution. By different ways we can represent. So basically we have I can say 7 concentration terms. Okay, I'll discuss one by one. So the first one is your mass percentage. Okay, first one is mass percentage. What's the formula here? Mass of the solute by mass of the solution into 100. Now remember, here it is mass of the solution. Next we have volume percentage, volume of the solute divided by volume of the solution into 100. Now I'll give you an example. Suppose I write a solution like 10% NaCl solution is there, and I write 10% W by W. So what does this indicate? This indicates that I have 10 gram of NaCl. Okay, and when I write percent, that means 100 gram is the solution mass. Okay, and 10 gram is NaCl mass. So what is the mass of the solvent then? You can easily calculate. Solvent mass is 90 grams. Right, now coming to volume percentage. So if you have 10% volume by volume NaCl, then what you will write? 100 ml is the mass of the solution. What is 100 ml here? 100 ml, sorry, not mass, volume of the solution. Okay, in that 10 ml is what? 10 ml is volume of NaCl. Okay, then you have 90 ml. 90 ml is equal to volume of the solvent. Clear? Now coming to mass by volume percentage. Mass by volume percentage is W by V. That means mass of the solute by volume of the solution into 100. Now let's take an example again here. 10% W by V if I write NaCl. Now what does that means? I have 10 gram of NaCl, okay, in 100 ml of solution. Okay, you can see this is in mass, the mass of the solute, and the mass of the, and we have volume of the solution. Clear? So this is very important. You have to understand what is the physical meaning of the concentration term. Then, because then only you can apply it while doing the numericals. Now parts per million is parts of the component by total parts of the component into 10 to the power of 6. Next, fifth one is mole fraction. So in mole fraction, what happens? Suppose you have two components. Okay, in a mixture you have two components A and B. Then mole fraction of A will be equal to number of moles of A divided by number of moles of A plus number of moles of B. Similarly, we have mole fraction of B is equal to number of moles of B divided by number of moles of B plus number of moles of A. If you have C, then that will be also added. Now here one important relation that you should know is XA plus XB should be equal to 1. Okay. Now it is a unitless and temperature independent concentration term. So now we have understood the 5 important concentration terms: mass percentage, volume percentage, mass by volume percentage, parts per million, and mole fraction. Okay. Now see, questions are definitely asked here, but the major quantities that you should know is molarity and molality. So let's discuss that in detail. What is molarity? It is denoted by capital M. It means that the number of moles of solute dissolved per liter of solution. In 1 liter of solution, how many moles of solute is present? How to write the formula? M molarity is equal to WB by MB into 1000 by VML. What is WB? Mass of the solute. MB molar mass of the solute, and V is the volume of the solution in ml. Okay, now units you can see. So actually see, the formula here can also be written as WB by MB. Okay, into 1 by volume of the solution in liter. If the volume in the question is given in ml, then you should multiply with this 1000 to convert it into liter. Okay, so what is the units then? Moles per liter, or you can write molar, capital M. Now what is the applications here? See, if two solutions are there, okay, you are diluting it, then what formula we use there? M1V1 is equal to M2V2. Now what is the application of this formula? See, for example, you have a certain solution A, okay, its molarity is M1 and the volume you have taken is V1. Now you added some more volume, okay, you change the volume, then what is the change in the molarity? If you want to calculate such questions, then you have to use the formula M1V1 equal to M2V2. Now there's one more type of question. Suppose you have A here one solution, B is one solution whose M2V2 is there. Now you mixed this one, okay. Now what you did, you mixed A and B. Then what is the new solubility or new molarity? If that type of questions are asked, then M1V1 plus M2V2 is equal to MF into V1 plus V2. These two formulas can be asked in your numericals, so you need to practice this one. Next, it is very important that molarity is a temperature dependent. Okay, why? See, when temperature increases, volume of the solution will increase, and if you see, if volume will increase, then what will happen? Inversely proportional, so molarity will decrease. So we can say that molarity is a temperature dependent function. Now let me give you a clear example. Suppose I have a solution of 2m NaCl. Now what does this term means? You have to be very clear here. 2m NaCl means what? That means you have 2 moles of NaCl in 1 liter of solution. Okay, this clarity has to be there. You should understand the application of that word. When I write 2m, if I write 10%, what does that mean? What is the significance of that concentration term? If you understand, then you can solve all the questions. Okay, let's move to now next concentration term, that is molality. Okay, now molality is what? Number of moles of solute dissolved per kilogram of solvent. Okay, that was molarity, was number of moles per liter of solution. Here molality is number of moles of solute per kg of solvent. Okay, there it was solution, here it is solvent, and it is denoted by small m. How to write the formula? M is equal to WB by MB into 1000 by WA in gram. WB and MB I have already discussed in the previous one. WA is the mass of the solvent in grams. Now its units will be moles per kg and small m or molar. Now it is temperature independent. See, as it is based on the mass and not volume, it is unaffected by the changes in temperature. Clear? Now suppose I write one example again, 2m NaCl. Now what you will understand from here, it means 2 moles of NaCl in 1 kg of solvent. Clear? So based on this, now let us solve a question here, okay, numerical. See, a solution of glucose, see, if you have understood the concentration terms properly, easily you will be able to solve this question. See, a solution of glucose whose mass is C6H12O6 and the molar mass is 180 gram per mole in water is leveled as 10% by mass. Okay, the density of the solution is 1.2 gram per ml. Then what would be the molality and molarity of the solution? Okay, so first of all, what is given? A solution of glucose is taken in water and is leveled as 10% by mass. Okay, this is very important, that you have 10% by mass. That means you have, what do you mean by that? You have you have 10% W by W. Okay, now see, 10% by mass means what? You have 10 gram of solute, that is glucose, in 100 gram of the solution, right? 10% means 10 gram of glucose in 100% of the 100 gram of the solution. So what is the mass of the solvent? Water. Why we are taking water? Because here it is given, it is dissolved in water. So what is the mass of the solvent now? 90 grams. Now see, if you want to find the molality, what's the formula for molality? Okay, just a minute. So what's the formula for molality? Molality is number of moles of the solute, okay, divided by mass of the solvent, right? Mass of solvent and into 1000 I have, right? So I already got mass of the solvent. I know the mass of the solute, that is 10 gram. Molar mass of glucose is also given. So directly we can calculate now molality. So let us see molality, WB by MB into 1000 by WA. So WB is 10 gram, right? Divided by molar mass, glucose mass is 180 into 1000 by 90. So 90 why I am taking? Because mass of the solvent, right? Total solution is 100 gram, 10 gram is solute, so 90 gram is solvent. So that is why 1000 by 90 and I'll get 0.617 m or molar. Now the next part of the question is to find the molarity of the solution. See, for molarity, what I need, if you just write down the values or formula, WB by MB into 1000 by volume of solution I need, right? Volume of solution is needed. Now what is the formula of molarity? It is number of moles, oh sorry, what's the formula of density? Density is mass by volume. Now see, volume will be equal to 1, then what? Mass by density. M is what? Mass of the solution. When it is given 10%, that means mass of the solution is 100 grams. And then you have been given with density. Density is how much? 1.2 gram per ml. So what is the volume of the given solution? The volume of the given solution is 100 by 1. Okay, so now let us solve this and calculate the molarity. Okay, so molarity, first we'll calculate volume, that is mass by density. So 100 by 1.2, which is 83.33. Now after that you'll calculate the molarity formula, WB by MB into 1000 by volume. So WB is 10 and molarity is, sorry, molar mass is 180 into 1000 by 83.33, which will give you 0.66 molar. Okay, so that is how you can see. If you don't know the meaning of 10% by mass, then you will not be able to solve this question. Okay, so that is why it is very, very important to understand the practical meaning of the concentration terms. Okay, now let us move to the next topic, that is solubility. What do you mean by the word solubility? Solubility means the maximum amount of a substance that can be dissolved in a specific amount of solvent at a specific temperature. Temperature should be fixed, and suppose you are fixing the amount of solvent, for example 1 glass of water, for example, then in that 1 glass of water at the same temperature, how much amount of solute can be dissolved, that is called as the solubility. So we will study solubility in two ways. The first one we'll study is solubility of solid in liquid, and then we'll study about the solubility of gas in liquid. Okay, so first we'll start with solubility of solid in liquid. So it depends what are the factors affecting the solubility of solid in liquid. The first factor is the nature of the solute. Now here it is very, very important that if you have a polar solute, okay, polar solute means what? What do you mean by the word polar? Polar means something which has a net dipole moment, right? Net dipole moment should be there. So if polar solute should be dissolved in polar solvent and a non-polar solute is dissolved in non-polar solvent. So there's a saying that like dissolves like. So polar will dissolve in polar, non-polar will dissolve in non-polar. So that is why, say if you see benzene is a non-polar compound, right? And water is a polar compound. So all the non-polar solutes will be dissolved in benzene but not in water, and similarly all the polar solutes will dissolve in water and not in benzene. Okay, next the factor is temperature. So the dissolution of solid in a liquid can be both endothermic and exothermic. Okay, it is not always endothermic, neither always exothermic. So if it is endothermic, okay, if the dissolution process is endothermic, then if you increase the temperature, solubility will increase. But if it is an exothermic, means delta H is negative, then solubility will decrease with the increase in temperature. If you increase temperature, solubility will decrease if it is an exothermic, and solubility will increase with temperature if it is a endothermic process. Next, pressure has no such effect in the solubility of solids in liquids, but pressure has a major role in the solubility of liquids and gases, which we'll study in the next slide. So now let's talk about solubility of gas in a liquid. Okay, it very, very highly depends on pressure. If you increase the pressure, the solubility will increase, and temperature, it will decrease if you increase the temperature. Okay, here it is constant. It is always that if you increase the temperature, the solubility will decrease for a gas in a liquid. Okay, and for solid in a liquid, it has to depend whether the dissolution process is endothermic or exothermic. But in gas, it is not like that. Whenever you increase the temperature, the solubility will decrease. Okay, so now here I can give you a very good example. If you know carbonated drinks, okay, carbonated drinks, so you might have observed that if you are drinking any cold drink, okay, you have just purchased it and you have it is cold, then you can find that that there's a burning sensation we get, right, due to the presence of carbon dioxide and all. That burning sensation will come better if it is a cold one, means when you're opening. Okay, after opening, if you have kept it for long days, then the story gets different. But the new bottle, if you're opening, if you're taking a cold bottle and if you're taking a warm bottle, then definitely I can say the solubility, that burning sensation, you will get more in the cold drink, because there the solubility of gas is more because temperature is low. Okay, and here in the warm bottle, in the room temperature bottle, this the burning sensation will be less because less carbon dioxide is dissolved due to the higher temperature. Okay, this is just an example. So now you can see here a diagram. Suppose you have a system here and this is a piston and you have put W1 here. So this line is what? So I can say this is air and this is water, for example. So when you have just given 1 W, there's so very less particles have dissolved. But when you increase the pressure, if you keep on adding more weights and piston goes down and the gas gets compressed, you can see more number of particles have now dissolved from here to here. Okay. Now let's talk about one very important law. See this particular law now, which says that if you increase the pressure, the solubility will increase. That particular thing is given to us by a law called as Henry's law. And let me tell you that this law is very important and will be asked in the exam. So please prepare its definition, statement, everything thoroughly. Okay. So I'm just putting here very important. Now let's talk about what is Henry's law. The partial pressure of the gas in the vapor phase is proportional to the mole fraction of gas in the solution. Okay, what it says, see, if you have a I can say if you have a gas, if you have a solution here where some gas is dissolved, so that gas will also evaporate, right? So when this gas evaporates, there is some pressure created here. Okay, so whatever pressure created here by the gas dissolved, that depends on how much gas is dissolved in the solution. It is very obvious. See, if more gas is dissolved, then more gas can evaporate. Okay, with time, if more gas will evaporate, they will have more pressure. So that is the Henry's law, which says that the partial pressure of the gas above the liquid surface is directly proportional to the mole fraction of the gas in the liquid. Okay, so here it is written like this: partial pressure is proportional to mole fraction of the gas. Partial pressure of the gas is proportional to mole fraction of the solute in the solution. To remove this constant, to remove this proportionality, we multiply a constant which is Kh, and that is called as your Henry's law constant. Now, if you see how I can write this one, Kh can be written as P by X. Here see, X actually represents solubility. Okay, X represents your solubility and X is your mole fraction here. By the way, let me just tell you all the terms here. What is P? P is the partial pressure. P is partial pressure and X is your mole fraction of the solute. Okay, so now if you see Kh is equal to P by X, so what do you understand? If Kh value is higher, X value will be lower, right? So that is the term here, as a higher value of Kh means lower solubility of the gas and Kh value increases with temperature. So if you remember just now we discussed that if temperature increases, solubility will decrease, right? That can also be connected here. When temperature increases, Kh increases, and if Kh increases, solubility decreases. Okay, so now you can see here the one graph for pressure and solubility. So I'll just erase this one. Okay, so you can see here that pressure is directly proportional to solubility. If you keep on increasing pressure, the solubility will keep on increasing. The point is temperature should be constant here. So you can see at different points as you are increasing the pressure. So for this pressure you have this much solubility, at this pressure we have this much solubility, like this. When you increase the pressure, the solubility keeps on increasing, right? So next we'll talk about some applications of Henry's law. Again, very important question. See, the first application is in the manufacture of soft drinks and soda water. The solubility of CO2 is increased by applying pressure. So if you have observed, okay, again we'll come to some carbonated drinks. If you have observed, when you open the carbonated drink for the first time, okay, when you have purchased it and when you're opening, you can see brisk effervescence, right? The gas will come out like this. That happens because the carbon dioxide is stored under the cold drinks under high pressure. Okay, now when you open the cap, you are actually releasing the pressure, you are lowering the pressure, so solubility of the gas will decrease. That means the gas cannot be more soluble now in the solvent, so it will start escaping, and it escapes in such a way that we find that effervescence when we open the cap. Next one is very important here, something about scuba diving. Okay, let us understand what is this one. See, when the scuba divers, if you have seen, they go down the ocean, okay, the sea or seabed, when they go down, the pressure increases. So as we have understood just in Henry's law, when pressure increases, so solubility will increase. So in the body, more amount of gases will get dissolved. So the oxygen cylinder which the scuba divers have, they have nitrogen, oxygen. Okay, so what happens, even more nitrogen will also get dissolved in the blood. Now when the scuba diver comes to the ocean, sorry, one second. See, suppose I'll draw here. See, this is the level. Okay, now suppose the scuba diver goes here. Here the pressure is more, so more amount of gas will be dissolved. Now after that, what will happen when the scuba diver comes to the surface level? Then as the pressure decreases, so the gas will dissolve, the solubility of the gas will be reduced, so gas will come out in the form of bubbles. Okay, like how you have seen the carbon dioxide, it comes in the form of bubbles. Similarly, all the gas dissolved will come out, and especially nitrogen will come out very fast, and they will form these bubbles, and they can block your veins and arteries or blood vessels. Okay, so that blocking of your blood vessels is a medical condition called as bends, and that gives a huge pain to the scuba divers. So that is why, to help you or to prevent this situation, what we do, in the oxygen cylinder of the scuba divers, helium gas is used. Okay, now helium gas, if you have seen, their KH value is very high and the solubility is very less. So when we go deep down the ocean, because of its less solubility, it gets less absorbed and less amount will be released when you come to the surface level, and in that way bends can be prevented. Okay, now coming to the third application. Okay, now coming to the third application is for higher altitudes. Now see, when mountain climbers and all trekkers, if you have seen, when they go to the higher altitude, there the pressure is less. Why? Because the height is less, so pressure is less. If pressure is less, solubility will be less, so less amount of oxygen gets dissolved in our blood. Okay, so now if less amount of oxygen gets dissolved, so our brain does not get enough amount of oxygen, and if brain does not get enough amount of oxygen, it loses its ability to think, and they get dizziness, and this medical condition is called as anoxia. Okay, so see, at higher altitude the partial pressure of O2 is low. As a result, there is a lower concentration of O2 in the blood and tissues of the climbers and people living at higher altitude. Okay, consequently they suffer from anoxia. So two medical conditions you have to understand. When for scuba divers it is bend, when they go down there is more solubility, or high, like the gases gets more soluble, and when they come up the solubility decreases, and that can cause the blocking of blood vessels leading to bends. And for that, what is the solution? You can use helium gas, which has very less solubility. And the second application is when you go higher altitude, due to less partial pressure, less oxygen get dissolved and our brain reaches less, I can say, the blood reaches the brain which has less oxygen present in it. Clear? So these are the applications of Henry's law. Now let's do a question on Henry's law. So the question goes like this, that calculate the solubility of CO2 in water at 298 Kelvin under 760 mm of Sg. KH value of CO2 in water at 298 Kelvin is this much. Okay, so what are the given values? You have been given with pressure, you have to calculate solubility, and the KH value is also given. So we have this very simple formula of Henry's law, P is equal to KH into X. So solubility X will be P by KH. So P is 760, KH is 1.25 into 10 to the power of 6. That gives you 6.08 into 10 to the power of minus 4. Now students, see, you have got calculators in your board exams, so you can definitely use it. So there is no tension if any big numbers come for calculation. You just need to know the formula and how to apply it. If you know that, calculations part is not a problem at all. Okay, now let's move to another very important topic, that is vapor pressure. Okay, if we understand vapor pressure, we can understand the upcoming topics. So what is vapor pressure? See, first of all, vapor pressure, to have a vapor pressure you need to have a closed container. Okay, imagine this is a closed container. Now what is happening here? You have kept some liquid, so the liquid will evaporate, okay, and it will create vapors here. Okay, these blue dots or these red dots which are already present, these are the vapors, right? This process is going on. What will happen? These vapors will go hit the container and then they will condense, right? Then they will condense. So there are two processes happening, evaporation and condensation. Now there will be a situation when the rate of evaporation and rate of condensation becomes equal, means how many particles are evaporating, that many particles are condensing, and that point of time when you have rate of evaporation is equal to rate of condensation, we call it as an equilibrium position. Okay, so at equilibrium position, you will have the liquid, you will have the vapor, and they are evaporating, they are condensing. So the process is going on, but the rate is constant, means the number of particles evaporating is equal to the number of particles condensing. Now let us take an example and understand this one. So imagine, suppose you have here 7 particles. Okay, I'm just drawing here, please understand. Okay, 1 2 3 4 5 6 7. Now what will happen? Some have already evaporated, and there are, suppose, 4 particles in the vapor phase. Okay, now what I'm saying, that the situation or the container is at equilibrium, then rate of evaporation is equal to rate of condensation. So what will happen? Suppose 2 particles are evaporated here. Okay, Now imagine what we have. See, in the liquid state, how many particles were present? 7. And in the vapor state, we had 4 particles initially. Now 2 particles have evaporated. If 2 particles will evaporate, what will happen? The vapor phase will have 4 plus 2, now 6. Okay, but at the same time, what will happen? 2 particles from the vapor phase will condense, right? So that means what? Here again, from this 4, 2 have went back here, so the concentration will remain same. Okay, the concentration of vapor phase and that of the liquid phase will not change, because the number of particles evaporating and number of particles condensing is equal. So at this point of equilibrium, when the rate of evaporation is equal to rate of condensation, whatever vapor is present and what pressure they are exerting on the liquid surface is called as vapor pressure. Okay, what is vapor pressure? Vapor pressure is the equilibrium pressure of the vapor above its liquid or solid state. So the vapors which are present, the system is at equilibrium, and at that time whatever pressure is exerted by the vapors on the liquid or the solid which is present below it is called as your vapor pressure. Now at equilibrium, what should be happening? The rate of evaporation equals the rate of condensation. Molecules in vapor phase collide with the walls and lead container, causing pressure. Evaporation and condensation occur at the liquid surface. So here you can see at the surface there is evaporation and condensation. Increasing the temperature increases the rate of evaporation and increases the vapor pressure. So if you increase the temperature, what will happen? More particles will evaporate and the vapor pressure will increase. Okay. So now let's talk about one of the most important law. Once we have understood the vapor pressure, we'll talk about now what is Raoult's law. Okay. See, Raoult's law is applicable in 2 conditions. What is it? See, when you have a solution where A and B are present and both A and B can evaporate. Okay, and there's one more condition in the solution when you have A and B. Okay, B can evaporate but A is not able to evaporate. Okay, this non-volatile solute and you have a volatile solute. So when you have both A and B, so A will evaporate and create some pressure here, so that is written as PA, and B will evaporate and create a pressure here, that is PB. Okay, so how do we write here? The pressure of A, okay, is proportional to the mole fraction of A in the solution. It's very similar to Henry's law. So the partial, but here what we are taking 2 volatile liquids. That's the difference here. So you can see that the partial vapor pressure of a component in a solution, means this PA, partial vapor pressure of the component in the solution, is equal to the vapor pressure of the pure component multiplied by its mole fraction. So PA is equal to P naught A XA. Now what is this P naught A? See, P naught A is a situation where you have, means if you just imagine that you have only A in the solution, okay, and A is evaporating here and creating some vapor pressure. So when you have only A, whatever vapor pressure it will create, that is P naught A. PA is the pressure of A when it is in the solution. P naught A is the pressure of A when only A is present. It's a pure form. So what I can write, PA is the partial vapor pressure of the component A, P naught A is the vapor pressure of pure component A, and XA is the mole fraction of A. So what I can write, PA is equal to PA, you can write down, see here, P total, means here I can write as this one is my P total, that is equal to PA plus PB. PA is equal to P naught A XA plus P naught B XB. Okay. Now coming to, for a solution with a non-volatile solute, if there is a non-volatile solute, then what will happen? P total is equal to P naught of the solvent and X of the solvent. Because see, if non-volatile solute is there, that means it will not evaporate. There is no PA here. You have only, okay, we'll take the different scenario because nomenclature is slightly confusing here. Let me tell you like this, that suppose you have a solution where A and B is present. A is evaporating, B is not evaporating. That means there is no PB, right? What is P total here? In this one you have only PA because B is not evaporating. So what I will get? P total is equal to only PA. And what is PA? We have just discussed P naught A XA. So when you have a non-volatile solute, P total is equal to pressure of the solvent only. And pressure of the solvent will be P naught of the solvent into mole fraction of the solvent. Okay, so this is very important from Raoult's law. Now let's discuss about ideal solutions and non-ideal solutions. If you have understood Raoult's law, then what are these ideal and non-ideal solutions? So the ideal solutions are those which will obey the Raoult's law, okay, at all concentrations and temperature. Means if I have taken A and B two components, the total pressure that I am calculating by using Raoult's law and the total pressure that I am measuring will be equal. Okay, so PA will be equal to P naught XA and PB will be equal to P naught B XB, and the total pressure will be equal to P naught XA plus P naught B XB. And but if it is a non-ideal solution, then the value will not be, means the solutions does not obey Raoult's law, and PA will not be equal to P naught XA and PB will not be equal to P naught B XB. Okay, this is clear. Now what is delta H mix? Okay, delta H mix means when you're mixing two solutions A and B, there will be no enthalpy, means no heat is generated, no heat is lost. So delta H mix is equal to 0. But for non-ideal solution, the delta H mix is not equal to 0. Then we have V mix is equal to 0, means whatever, for example, you have taken 2 ml of A, 2 ml of B, and when you have added them, you got 4 mole. So initial also you had 4, and after mixing also you had 4. So that is why there's no change in the volume in ideal solution, but in non-ideal solution does not equal to 0. Now examples are very important here and can be asked. So for benzene, for ideal solution, the example is benzene and toluene, ethyl iodide, ethyl bromide, N-hexane, N-heptane. These all examples are very, very important. But for non-ideal solutions, you can have acetone and aniline, chloroform and diethyl ether, water and nitric acid. Okay, so many examples are there. Okay, now let's talk about non-ideal solution. See, so as I told you, it is not, the total pressure is not equal to P naught XA and P naught B XB. If it is not equal, it can be either higher or lower than P total, right? So that is where we get positive and negative deviation. So if the total pressure, okay, one second. Okay, so if the total pressure is greater than the calculated value, okay, what pressure you are measuring, that is more than the calculated value using Raoult's law, then that is an positive deviation. Okay, and in the negative deviation, the total pressure will be less than the calculated value. Okay, now when you have mixed A and B, okay, you calculated that the partial pressure should be 5 atm, for example, but you are getting a value of 7 atm. That means it is positive deviation. You have calculated 5 atm, but the pressure that you are getting is 3 atm, then it is a negative value, negative deviation. Now why this positive and negative deviation happens? See, understand, if you understand it logically, it is very simple. See, I have mixed A and B. Okay, now if this A and B interactions is very weak, means A and B are like hating each other, they don't want to stay with each other, their interactions are very weak, then what will happen? They will try to escape, right? They will try to escape from each other. A will evaporate faster, B will evaporate faster, because they don't want to stay together, right? So when they escape, more amount of A vapors has formed as per the calculated value. Suppose you have formed that 5 will form total, okay, but now since they are not, the interaction is very weak, A will evaporate faster and give you more A, B will also evaporate faster, and more pressure will be created in the vapor phase. So that is why the total pressure will be more than the calculated value. So what is the, so here what we can talk about their interactions, the new AB interactions between A and B is very weak than the old AA and BB interactions. Whatever, see, so earlier when you have, see, okay, now see, when you have only AA, there will be some interactions, you would have BB, there will be some interactions. But when you mix this AB, the interactions is very weak. So A will also evaporate, B will also evaporate, they are not holding each other. So that is why what will happen? The pressure in the vapor phase will be more, the particles in the vapor phase will be more, and the more vapor pressure will be created. Right? This is clear, and that is why we get a positive deviation higher than the expected value. But on the other hand, imagine if A and B is having very strong interactions. Okay, they're very close to each other, they don't want to leave each other and go. So A will also not evaporate much, B will also not evaporate much. So the expected value, they are now not evaporating because the interactions are very, very strong. So what will happen? When the vapors, the number of vapors that is created will be less than the expected value, and that is why we get a negative deviation or less value than the Raoult's law. Okay, so positive deviation, weak interaction, negative deviation, strong interaction. These 2 points you have to remember properly. If you understand the logic, you can definitely remember it. Now next points what we have, this is very easy to remember because it is positive. You will have delta V mix, V mix greater than 0, and here V mix less than 0, here H mix is greater than 0, here H mix is less than 0. Here dissolution process is endothermic, as you can see delta H value is higher, so when you mix it, heat will be required, and here heat will be released. Then this form minimum boiling azeotropes. So this point we'll understand in a while when we talk about azeotropes. Now the next part is very important, example. So for positive deviation, examples are ethanol and water, ethanol and acetone, CCl4 and CHCl3, CCl4 and benzene, CS2 and acetone. These are all examples of positive deviation. Now coming to negative deviation, CHCl3 and that means chloroform and acetone, chloroform and nitric acid, acetic acid and alcohols, and you have chloroform and benzene. So these are all examples of negative deviation. Now let's talk about the graph. So you can see the graph can be asked in the exam. So PS prepare graph thoroughly. So if you have, like, see, what is the, for ideal solution, P total is equal to P naught A XA plus P naught B XB. Okay. Now when you have only A, okay, there is no B. At that point, if XA is equal to 1, then what is the value of P total? P total is equal to P naught A because XA is equal to 1. So imagine when you have this point, when only x1 is present, at that time what is the pressure? P naught 1. Now 1 has gone to you can see the value of x1 is, from 1 it has come to 0, right? And we know that pressure is proportional to x. So as the mole fraction of 1 is decreasing, the pressure is also decreasing. You can see here. Now coming to x2, here 0 to 1 the mole fraction is increasing, the pressure of B is also, or 2 is also increasing, and then this point, this line, if you join, you will get the total pressure. Now what is the point for positive and negative deviation? The same graph, but in positive deviation the pressure will be higher than the expected value, but in negative deviation the pressure will be lower than the expected value. Okay, this is about non-ideal solutions. Now I told you we'll talk about azeotropes in a short while. So what are azeotropes? See, azeotropes is a special type of binary mixture. Okay, it's a special condition. What is that special condition? That it have the same composition in the vapor phase and in the liquid phase. Okay, the vapor phase and liquid phase composition is exactly same, and that is why you cannot separate it by distillation. Okay, and the whole entire solution A and B, when you have mixed, right, the A and B will have the same boiling point. Okay, their boiling point will be same. So that is why also you cannot separate it using distillation. So that type of solutions are called as azeotropes. So these are liquid binary mixtures which distill over without any change in the composition. Okay, from solid to liquid, from liquid to vapor, there is no change in composition. Now let's understand what is minimum boiling azeotrope and maximum boiling azeotrope. See, you have mixed A and B. Okay, A will have a separate boiling point, B will have a separate boiling point. But when you mix them, if their boiling point, the I can say the new boiling point of the solution, they will have one boiling point. Okay, when you have mixed it in the azeotropic mixtures, they have single boiling point, both A and B. That is the speciality about these mixtures. Now this new boiling point, if it is less than the individual values, for example A is 100, B is 90, and we have mixed A plus B, it is having 60. Okay, less than both the individual values, then it is called as minimum boiling azeotrope. The solution has a boiling point lower than either of the components of the solution. If you are mixing A and B, one is 100 and another is 90, and the final value when you mixed it, it is 120, more than both the values, then it is called as maximum boiling azeotrope. Now how this will happen? See, when your boiling point is decreased in minimum boiling azeotrope, what will happen? The boiling point will decrease. Now why does that happen? See, when the A and B is having very weak interactions, or they have positive deviation, so because already A and B interactions is very weak, they want to evaporate, so with less temperature only they can evaporate faster, right? With very less temperature they can evaporate. So when the AB interactions is weak and when they show positive deviation, you will find minimum boiling azeotrope, okay, formed by liquid pairs showing positive deviation. On the other hand, when the two groups, 2A and B, is very tightly attached, they are very strong interactions, so you have to give a higher temperature to boil them because the force of interaction is very high, very strong. So that is why I can say that maximum boiling azeotrope will be obtained for those solutions which show negative deviation. Okay, next we have example here, ethanol plus water. The boiling point of the solution is 351.1 Kelvin and the composition is 95.6% ethanol and 4.4% water. Now talking about the example of minimum boiling point or azeotrope, it is nitric acid plus water. The boiling point is 393.5 and 68 point of HNO3 and 32% of water. So there is only one example, and yes, you need to remember the composition, exact composition, because if you just take simple nitric acid and water, you will not get azeotrope. You have to take at this particular composition, 68% and 32%, then only you will get the azeotropic mixture. Okay, clear? Fine. Now let's talk about the heart of this chapter, most important point of this chapter, that is colligative properties. See, colligative properties are those properties of the solvent. Whose properties? Of the solvent which depends on the amount of solute added. How much solute you have added, based on that those properties will change. These are called as colligative properties. So how many colligative properties we have? The first one is relative lowering of vapor pressure, elevation in boiling point, then we have depression in freezing point, and osmotic pressure. So we'll study all of them one by one. So let's start with relative lowering of vapor pressure. So understand that whenever you add a solute to a solution, the vapor pressure will decrease. Okay, what will happen? Suppose you have a pure solvent A. Okay, here you had a pure solvent A. Okay, now you added a solute here B, which is non-volatile. Okay, see, if you are adding a volatile solute, then AB interactions will be there. It can be positive, negative, or ideal. Vapor pressure may increase, decrease, anything will happen. But if you have added a non-volatile solute, then guaranteed the pressure will decrease. Now see, when you have added a non-volatile solute here B is not creating any okay, let me just give you a case study here. We'll go case by case. See, first of all, I give you numbers, okay, so that we can understand it better way. Suppose first of all you have a solvent is present A, okay, and it is creating some vapor pressure here P naught A. If only A is present, we will name it as P naught A. So what is the pressure of P naught A? Let this value be 10. Okay, and how many particles? So evaporation is a surface phenomenon, right? So what will happen? These particles which are present at the surface will evaporate. So 1 2 3 4 5 6 7 8. So just imagine that you have 8 particles on the surface which is evaporating and creating a pressure of 10 atm. Okay, or let us for easy understanding, let us take it as 8 atm only. Okay, so 8 particles are evaporating and the pressure created is 8 atm in the vapor phase. Now what you did, you add a solute to it. Which solute? Solute B. Okay, now your same container I am taking. Here A is present. You added a non-volatile solute B. Non-volatile solute B is added. Now what will happen? You have these 8 molecules, 1, 2, 3, 4, 5, 6, 7 and 8. Now what will happen? These B particles in the this one will occupy some of the surface phenomenon. Okay, they will suppose this particle is B, then this particle is B, and then this particle is B, right? So you can see that the number of particles on the surface has now decreased because of this addition of solute B. So now how many particles can evaporate? 1, 2, 3, 4, 5 particles can evaporate. So what is the pressure now? But here only A is present now, okay, because B is non-volatile. A will not evaporate, only B will evaporate. So sorry, B will not evaporate, only A will evaporate, right? So the pressure of A is now 5 atm. You see the difference here? When you add a solute, the pressure of the solvent always decreases. The reason being that the solute particles occupy some of the surface. Okay, so now evaporation is a surface phenomenon. Now earlier how many particles were able to evaporate? Now less than that the number of particles are evaporating. So because the less number of particles are evaporating, so less number of vapor will be created and the vapor pressure decreases. So always remember, whenever you add a solute to a solvent, a non-volatile solute, okay, volatile solvent, that can happen positive and negative deviation. But if you are adding a non-volatile solute, the pressure will always decrease. Okay, this is the first important thing. Now let's understand this point, that is relative lowering of vapor pressure. So when you added, okay, so the relative lowering vapor pressure is equal to the mole fraction of the non-volatile solute. So what is here P01? See, P0 is the pressure of pure solvent 1. Now what is P1 here? P1 is the pressure of the solution. Means when you have added the solute, what is the new pressure? Okay, so I can say it is the pressure of solvent, okay, which is denoted by 1 in solution. Means when you have already added the solute, and that is equal to the mole fraction of the solute. What is W2? W2 is the mass taken or mass of the solute. Okay, and M2 here is what? M2 is the molar mass of the solute. Okay, molar mass of solute. And similarly W1 is the mass of solvent, and M2 is the molar mass of solvent. Let me just write down. Yes. Okay. Now a question may arise, ma'am, X2 formula should be N2 by N1 plus N2, right? Then where is this N2 here? So basically when you are very dilute solutions you are considering, this N2 is ignored. Okay, why? Because N2 is very less than N1. So we put the formula N2 by N1, so W2 by M2 by W1 by M1. And remember here, this part, this first numerator, P01 minus P1 is called as the lowering of vapor pressure. That is not a colligative property. The relative lowering of vapor pressure is. So for calculating of relative lowering of vapor pressure, you have to divide it by P01. Okay. So let's do a question from this one. Okay, see, a solution is prepared by dissolving a 10 gram of a non-volatile solute in 200 gram of water. Okay, so let's read the question and just write down the values that we are crossing. So what is the mass of the solute? So mass of the solute taken is 10 grams. And what is the mass of the solvent? Mass of the solvent taken is 200 grams. Now what we have, it has a vapor pressure of 31.84 mm of Sg at 308 Kelvin. So what is the pressure of the solution? This solution pressure means you have to write PA. PA is how much? 31.84. Calculate the molar mass of the solute, the vapor pressure of the pure solvent. So P0A value is given to me as 32 mm of Sg. So you can clearly see here, now when you had only A, pressure was 32. Now when you added a non-volatile solute, the vapor pressure of A decreases to 31.84. So you have to calculate the molar mass of the solute. Clear? And what is, since this is water, the solvent is water, so what is the molar mass of Ma or solvent? That is 18 gram per mole. Right? Now let us write the formula. We have this formula, P0A minus PA is equal to WB by MB into MA by WA. So what is P0A? That is my 32 and PA is 31.84. P0 is again 32. Here MB is, sorry, WB is 10 gram. MB I have to calculate. 18 gram is this one, and that is MA is 18 gram and WA is 200 gram. Now when you calculate this one, MB value, molar mass you will get is 180 gram per mole. Okay. Now let's talk about elevation in boiling point. See, the boiling point of a solution containing a non-volatile solute is always higher than a pure solvent. So as we discussed that the vapor pressure will always decrease. Similarly, when you have a pure solvent and you add a solute to that, the vapor pressure, when you add a solute to that, now it is a solution. Now this solution boiling point will always be more than the boiling point of the pure solvent. Let me repeat it. Suppose you have a pure solvent, it is having a boiling point. Now when you added a solute, okay, now it has become a solution, added a non-volatile solute. Now the boiling point of this solution will always be more than the boiling point of the original solvent. Now what is the reason for that? Let us understand first. See, what is the definition of boiling point? For that you should know. See, boiling point is that temperature at which the vapor pressure of solvent, okay, is equal to the atmospheric pressure. Okay, the temp means you are boiling the water. Okay, it is creating vapor pressure. When the vapor pressure is increasing because more water is evaporating, a situation comes when the vapor pressure of the liquid or the vapor pressure of the solution is equal to the atmospheric pressure. At that time, that temperature is called as boiling point. Okay, so now let us see that with the graph. The first thing we have understood that the vapor pressure is from the first colligative property, that the vapor pressure of the solvent is more than the vapor pressure of the solution. I have already explained you the reason, because some of the particles are covered by the by the solute particles, so less number of molecules can evaporate. So that is why the vapor pressure of the solution is less than the vapor pressure of the pure solvent. So you can see in the graph, and we have also understood one thing, that if temperature is increases, vapor pressure also increases. So now you see this one is the vapor pressure of the solvent, okay, and this graph is the vapor pressure of the solution. Solution is less than that of the solvent. Now as the temperature is increasing, the vapor pressure is increasing. Now this is the atmospheric pressure. Okay, now see that solvent, when the vapor pressure of the solvent and the atmospheric pressure matches, that is your boiling point. But since here the vapor pressure of the solution is already less, it takes more time for the solution to reach the atmospheric pressure. So that is why you need to heat more, so the boiling point of the solution increases. So what's the formula? Delta TB. Okay, this value, the difference in the new boiling point and the original boiling point, is called as delta TB. It is TB minus T0B is equal to KB dot M, where KB is what? KB is your molar elevation constant, or it is also called as ebullioscopic constant, and it is for a particular solvent, the value is fixed, and M is the molality of the solution. and T naught B is what? T naught B is boiling point of solvent. Okay, and TB is what? It is the boiling point of solution. Okay, clear? Now let's talk about one question from here. See, calculate the molar mass of a compound when 6.3 gram of it is dissolved in 27 gram of chloroform. Okay, so what are the values given to us? 6.3 grams of what? The solute is 6.3 grams is dissolved in 27 gram of chloroform. Okay, to form a solution which has a boiling point. So the solution boiling point is how much? 68.04 degree Celsius. The boiling point of pure chloroform, so that means T naught B is how much? 61.04. You can see as you have added the solute, the boiling point has increased. Okay, and Kb value is given to me as 3.63. So now we can easily calculate and put the values. So you can see delta TB is equal to TB minus T naught B. So that value is 68.04 minus 61.04, that is 7 degrees Celsius. Now delta TB is equal to Kb into M. So that is equal to Kb into WB by MB into 1000 by WA. So you will get here MB value. How can I calculate? So you can see Kb into WB into 1000 by delta TB into WA. So all the values I have substituted here. You can see Kb value is how much? 3.63. WB is how much? 6.3. Then you have 1000, and then here this Kb will be delta TB will come here, right? If I multiply this one this side, and delta TB is 7 degree, and then WA is 27. Here I have given. So the total value MB, if I calculate, it comes out to be 121 gram per mole. Okay. Now let's go to the next one, that is depression in freezing point. So if you have understood the concept of, I can say, elevation in boiling point, it is very similar. So whenever you have a solvent, okay, its freezing point is there. When you add a solute, the freezing point will decrease. The freezing point of the solution will be less than the freezing point of the pure solvent. So the freezing point of a solution containing a non-volatile solute is always lower than that of the pure solvent. Now what is Kf? Kf is the molar depression constant, and the formula delta Tf is equal to T naught F minus Tf, because for the solution freezing point is less than the original value, right? And here you have delta Tf is equal to Kf into M, where M is molality, and the formula goes. Now let's understand this through a graph. See, as I tell you, what is then freezing point? Freezing point is that point or the temperature when the vapor pressure of the liquid is equal to the vapor pressure of the solid. Okay, now see, this is the solvent vapor pressure. Okay, solid solvent vapor pressure. Now this is the vapor pressure of the solution, and this is the vapor pressure of the solvent. Now whenever this is meeting, this is at this temperature, this point, that is your T naught F. Now when the vapor pressure of the solution is meeting the graph or the vapor pressure of pure solvent, that is TF, T naught F and TF. So that will give you the depression freezing point T naught F minus TF is equal to Kf dot M. Okay, now let's do a question from here also. You have 18 gram of a non-volatile solute, okay, dissolved in 200 gram of water, okay, and the solution freezes. What is TF value? 272.07 Kelvin. Calculate the molecular mass of the solute. Kf value is 1.86 Kelvin kilogram mole inverse. Okay, so how we can calculate? Delta Tf is equal to T naught F minus Tf, and 273 minus 272.07, that is 0.93 Kelvin, and delta Tf is equal to Kf into M. So I can substitute what is the value of delta Tf. So for water, you know, right, the 0 degree Celsius or 273 Kelvin, the correct value is 272.07. So delta Tf I have already calculated. Kf value is given in the question. WB I know 18 gram. MB I have to calculate 1000. WA is 200 grams, right? So just substitute everything, and then you will calculate MB as 180 gram per mole. Okay. Now let's see the fourth colligative property, that is osmotic pressure. So before understanding osmotic pressure, let's first talk about what is osmosis. So see, when you have two solutions A and B, okay, if you have two solutions A and B, okay, now A is suppose concentrated solution, okay, and B is a diluted solution, okay, that means what? the solvent, here solvent is more, here solvent is less. So what will happen? The solvent will move from B to A through a semi-permeable membrane. Okay, so the movement of solvent molecules from its lower concentration, okay, in the diluted solution the solvent concentration is more, okay, but you see the movement of solvent molecules from its lower concentration means diluted solution, from the diluted solution to a higher concentrated solution, means to a concentrated solution, from diluted solution to concentrated solution, the movement of solvent particles through a semi-permeable membrane. Okay, so what is osmosis? It is the movement of solvent particles, okay, not solute particles, from a diluted solution to a concentrated solution through a semi-permeable membrane. Now this semi-permeable membrane, why do we call it? Because it allows only the solvent particles to pass and not the solute particles to pass through it. Now what is semi-permeable membrane? Which allows only the movement of solvent particles, as we have discussed. Now this semi-permeable membrane can be natural or artificial also. Example of natural semi-permeable membranes are parchment paper, cellophane paper, etc. And for artificial, it is a film of gelatinous precipitate of cupric ferrocyanide. Okay, this is what we have prepared in the labs. Now we'll understand what is osmotic pressure. So we have understood that when there's a concentration difference, the solvent particles will move from diluted to concentrated solution. Okay, it will pass from that. Now if you apply the pressure on the concentrated side, okay, the water is flowing from this side to this side like this. Okay, now if you apply a pressure here to stop the osmosis, then that is called as osmotic pressure. Okay, what is it? It can be defined as the extra pressure applied on the solution side to stop osmosis, that is the flow of solvent from lower concentration to higher concentration, is denoted by pi. Okay, so if see from here, suppose this is happening, okay, thus here the osmosis is happening. Now if I apply certain pressure here on this part such that the osmosis just stops, then we call it as osmotic pressure. Pi is equal to C dot R dot T. C is concentration, R is gas constant, and T is temperature. Now let's talk about what is applications of this osmotic pressure. So it is widely used to determine the molar masses of the proteins, polymers, and other macromolecules. Now what are the advantages of this osmotic pressure? Why it is a preferred method for calculating the molecular masses of macromolecules? The first thing, it is because it is calculated at room temperature. Second thing, it uses molarity instead of molality. And then as compared to other colligative properties, its magnitude is large even for very dilute solution, means calculation becomes easier. The values that we get is very large values. Now let's talk about reverse osmosis. See, osmosis was happening in this direction. Osmotic pressure, you applied some pressure to stop the osmosis. Now if you apply pressure greater than the osmotic pressure on the solution side, more pressure if you apply, osmotic pressure is just to stop it, but if you apply pressure more than the osmotic pressure, then from this side the solvent will start flowing. From the concentrated side to the diluted side, the direction of osmosis will change, and that is called as your reverse osmosis. So applying a pressure greater than the osmotic pressure reverses the flow of the solvent, and this I can say mechanism is used in the desalination of water. Okay, now we'll talk about something called as isotonic solutions. If two solutions have the same osmotic pressure, then we call them as isotonic solutions. So example, so if there is two isotonic solutions, you are having a semi-permeable membrane, no osmosis occurs. Here example is the fluid inside the blood cells is isotonic with 0.9% of NaCl solution. So our blood osmotic pressure and the NaCl solution of 0.9% will have the same osmotic pressure. Then this solution is called as normal saline, and it is safe for intravenous injections. Now what is hypertonic solution? So solutions having higher osmotic pressure than the cell fluid. Okay, means if you are comparing to, here the reference is cell. So if the outside solution is having a higher osmotic pressure than the cell, then we call that solution as hypertonic solution. Now what will happen in this NaCl concentration? So if you see pi is equal to CRT, right? If the osmotic pressure of the solution is more, then definitely concentration will be more. So the NaCl concentration in the solution will be more than that of the present in the cell. So if that is concentrated, then what will happen? If this one is having more concentration, then this is diluted, right? So if you keep a semi-permeable membrane between them, or the cell itself has a cell wall which is a semi-permeable membrane, the water will flow out of the cell because this is diluted, this is concentrated, so water will start flowing outside and the cell will shrink. Now on the other hand, if you have a hypotonic solution, means you have a cell here and the concentration of this one, the outer one, is the solution is having lower osmotic pressure, means this outside solution is having a lower osmotic pressure, means its concentration is also less and the cell concentration is high. So what will happen? Osmosis will happen in this direction. Okay, so NaCl concentration is less than 0.9% and the effects will be the water will flow into the cells and the cell wall will swell, the cell will swell. Okay, now let's talk about the last topic, that is abnormal molar mass. Now see, we generally consider non-volatile solutes, right? We add the non-volatile solutes, and colligative properties is what? It depends on the number of particles and not on the nature of the solute particles. Now suppose you have added a solute, one solute you have added, but what happens if it got into the solution and it dissociated and it became two particles? Okay, then the colligative property that you calculate will be different from your imagined value. For example, if I add two particles, certain value I will get, but now that two particle became four particle after getting into the solution, then the colligative calculation that I'll get will be different. So this happens, this abnormal. So now see, what is our, if you see any colligative property, delta TB is equal to Kb into M. So for example, that is equal to Kb into given mass by molar mass into 1000 by mass of the solvent, right? Now, and we know that this delta TB is what? Is a colligative property, and we know that colligative property is proportional to number of particles. Okay, or so now what happens? Suppose any solute that you have added is undergoing dissociation, means it is breaking. For example, KCl. If you add KCl, what will happen? KCl will dissociate to give you K plus and Cl minus. So the number of particles has increased. So if the number of particles will increase, colligative property will increase and the calculated molecular mass value will decrease, right? So what is your expected value? If the solute is undergoing dissociation, then what MB or the molar mass you will calculate will be less than the correct value. Similarly, if the solute is undergoing association, you have added two particles, but after going to the solution, they became one particle. They have undergone association. In that case, what will happen? When they undergo association, so then what will happen? The number of particles will decrease, colligative property will decrease, and molecular mass calculated will be more than the expected value. So this abnormality or this mistake in molar masses calculation that happens due to the association and dissociation of the solute particles is called as the is called as abnormal molar mass. Okay, so if you have higher values, then you will observe, like in case of association, the values will be higher than the expected value, and in case of dissociation, the values will be lesser than the expected value. Then how to correct it? How can we get the correct values then? So for that, we have a solution, that is Van 't Hoff factor. Now it is the ratio of the observed value and the colligative observed value and the calculated value. Okay, I is equal to what? Observed value by calculated value, or you have normal molar mass by observed molar mass, or the number of particles before and after dissociation divided by moles of the particles before association or dissociation. So for example, you can see here, suppose you have this one, NaCl. Okay, so what is the I value? Number of particles after association will be 2, number of particles before dissociation is 1, so 2 by 1 is 2. K2SO4, I value is 3. Al2SO4 whole 3, I value is 5. Okay, now all our colligative properties formulas will get modified. You just have to multiply one I before the formula. So delta TB becomes IKBM, delta TF becomes IKFM, pi becomes IC dot RT, and RLVP, relative lowering of vapor pressure, becomes I dot X2. Okay, so now let's solve a question from here. You can see, okay, the question is, before that I want to just note down one formula here. So please note down that, one second. So for I means if alpha is, means if the association is taking place, okay, for association, alpha value is I minus 1 by n minus 1. Okay, I'll write it once again, one second. See, for association, alpha association is equal to I minus 1 by n minus 1. And if the solute is undergoing dissociation, then alpha is equal to I minus 1 by n minus 1. Okay, so that is there. Now we can do this question. See, a 0.01 m aqueous solution of AlCl3 freezes at 0.068 degree Celsius. So what is molality here? 0.01 and the temperature is 0.068 degree Celsius. Calculate the percentage of dissociation. Kf of water is 1.86 Kelvin kilogram mole inverse. Okay, so you can see here, we have this formula, calculate the percentage of dissociation. So first of all, your value you have to calculate is I value. You have seen that freezes as 0.068 degrees Celsius, so I can calculate delta TF. Delta TF value will be what? TF, T naught F minus TF, okay, that is equal to 0 minus 0.68, okay, that gives me plus 0.68. Then I value is there, Kf value is 1.86 and molality is 0.01. So from that I can get I value is 3.65. Now if you see alpha association value is what? I minus 1 by n minus 1. So 3 point, sorry, okay, so AlCl3 here, okay, this is for dissociation, right? So this is n minus 1. We'll get I minus 1 by n minus 1. So I have I is 3.65 minus 1. So n is what? The number of particles that is generated here. So for AlCl3, n value is equal to 4. So 4 minus 1. So you can substitute it and you'll get 0.883. So what is the percentage? Just multiply it with 100. You will get 88.3%. Okay. Yes. So students, this was the one-shot revision of solutions chapter, covered every concept. Now please wait for the next video which comes under the most important questions. So if you have understood these concepts and done all the questions from this chapter and this chapter is done for you, majorly focus on the examples. Okay, from here examples are very important. Colligative properties is the heart of this chapter, so prepare as many questions. The reasons of colligative, why the boiling point increases, why the vapor pressure decreases, why the freezing point decreases, Henry's law, Raoult's law. These are very, very important topic. And one more important suggestion for Henry's law and Raoult's law, see your textbook and whatever definition is written there, please remember that only, okay, because you should not be writing it in your own language. To prepare definitions thoroughly from NCERT. Okay, that's all my dear children. Thank you so much and I hope this video was helpful. If you liked it, just subscribe the channel and like the video. And yes, this channel is going to be your savior for your KCET and PU2 2026 examinations. So please subscribe the channel. Thank you. Bye bye and take care.